Shown here is our presentation outline. We'll first give a few brief slides that will show the ways in which Flow3D can be applied as a tool for hydraulics projects related to spillways and fish ladders. We'll also present validation cases for our advanced hydraulic models, including sediment scar and air entrainment. Next, we'll go ahead and show you two successful examples of applying simulation to real-world projects. The first project is the renovation of a fish ladder at 3rd Dam on Soms Brook in Somsville, Maine. This was done by John Richardson of Blue Hill Hydraulics for woodlot alternatives. The second project is to determine if the spillway structure at Smith Mountain Dam, located on the Roanoke River near Roanoke, Virginia, would be adversely affected by the new PMF flood conditions. The project was done by Dan Gessler of Alden Research for American Electric Power. At the end of this presentation, we'll close with questions and answers, which will be handled through the Q&A option at your right in the GoToWebinar software. We'll answer as many questions as possible. Also note that any questions that do not get answered will be answered later and sent out to all attendees via email. As you can see here, Flow3D can simulate many flow problems in hydraulics. Simulation with Flow3D will help optimize hydraulics designs and lower costs. Traditionally, when designing a hydraulic structure, a physical model needs to be constructed and analyzed. These projects are expensive to set up, both in terms of the time and materials required. Project costs are significantly reduced, however, when you use simulation. This is because setup time is minimal and materials and assembly is no longer required. Also, through simulation, you eliminate scaling issues associated with physical models. Flow3D applies unique modeling principles that differentiate it from other applications and enhances the accuracy of the results. Traditional 1D and 2D codes don't provide a full detailed analysis of flow currents and flow surfaces. Flow3D simulates the entire flow process so that these important details are not neglected. Advanced physical models are also included that allow the prediction of air entrainment as well as sediment scar. How can hydraulic structures be optimized? Now, not only is Flow3D versatile in its range of hydraulic projects, it's also powerful in its modeling ability within any given application. Flow3D addresses a wide range of design problems in hydraulics engineering. Users can increase the capacity of existing infrastructure in hydropower plants. They can develop novel approaches to modeling fish passages. They can design intakes that minimize the head loss. They can develop improved four-way designs and tail race flows. Users can also analyze scar and deposition and evaluate the air entrainment. I will talk about some of the advantages of Flow3D. Flow3D has many advantages, but the most important ones that we would like to point out in this presentation are accurate fluid advection and ease of meshing with our free gridding technique. True WOF is an advanced volume of fluid technique that distinguishes us from other volume of fluid approaches. It enables precise free surface interface and accurate fluid advection that is critical to the accurate tracking of waves and hydraulic jumps. Shown here in this animation is the flow released from a spillway. Note the complex flow patterns and surfaces that are generated. Please bear with us if you cannot see the presentation, if you cannot see the animation play clearly on your screen. Sometimes these animations slow down over the internet. Another advantage that Flow3D has is in its meshing and geometry features. Our favor fractional area volume obstacle representation method permits true representation of a complex geometry in a simple Cartesian mesh. As a result, Flow3D can be used to simulate flow in complex hydraulic structures accurately and efficiently. In Flow3D, please bear with us for a moment here. We are back here. In Flow3D, we use a structured mesh that overlays the imported geometry. Generating a mesh is as simple as overlaying it on the geometry and defining a level of resolution. Our proprietary favor method defines fractional areas and volumes within individual cells, enabling smooth and accurate representation of the complex geometry. In a body-fitted meshing system, one has to spend a lot of time in uniformly meshing complicated geometries. However, with the favor method, the advantage of using structured grids is further enhanced, bringing more focus to design since the designs are free of the mesh and can be evolved at less time and expense. I will now pass the controls to Travis, who will cover the rest of the presentation.
Thank you, Cheyenne. Bear with us while we get the presentation. Try the first one. Good morning, everyone. Sorry for the brief delay there. I'd like to cover our sediment scour hydraulics model. And the next two slides are a part of the validation of our sediment scour model. Scour and deposition are an important consideration in the design of bridges, dams, and reservoirs. The sediment scour model in Flow3D enables users to study the erosion and deposition of sediments caused by powerful currents and complex flow patterns. Figure 1 shows the profile of the experimental flume for a submerged horizontal jet. Water enters the flume through a narrow slit under pressure. The resulting two-dimensional sheet of water flows over a solid apron before contacting a packed bed of sand. The channel is wide enough so that there are three-dimensional effects that can be neglected near the middle of the flume. The scour profiles were measured down the center line. Figure 2 shows the time evolution of the packed bed profile based on experiment. The column of plots at the right shows the predicted profiles from Flow3D simulation. The domain has been truncated in these plots so that only the edges of the apron and the first section of the bed are visible. The shape and the height of the predicted bed profiles compare well to the experimentally observed sand bed. The plot shown is the depth of the deepest part of the scour hole and the height of the highest part of the deposited ridge. The experimental and predicted results are compared. The simulated height of the deposited ridge is predicted very closely to that of experiments, while a simulated scour hole is slightly over-predicted compared to that of the experiments. Remember that the scour lift model is empirical, and there is a parameter that represents a probability that the particle of sediment is lifted away from the packed bed interface. Adjustment of this value may be needed to more accurately represent the lifting process at the packed bed interface. Another hydraulics model that we have is air entrainment. Here we are looking at a validation of our air entrainment model. Air entrainment can have positive and negative effects. It may help sustain growth of microorganisms, which is beneficial to life and may cause downstream bulking and overtopping structures, which can be damaging. Flow3D's air entrainment model determines quantities of air entrained and its volumetric bulking effects. This test case involves a closed conduit. The conduit is inclined with respect to the horizontal. At the lower end of the conduit is immersed in water with a hydrostatic head above the top edge of the outlet. At the inlet, water enters with an assigned depth and rushes down the conduit under the action of gravity. A hydraulic jump develops about a third of the way down the stream from the inlet. For simplicity, we have elected to model the circular conduit with a two-dimensional vertical slice through its center. Figure 1 shows a snapshot of the computed result at a quasi-steady-state condition. There are some unsteadiness associated with the hydraulic jump, as there should be, but the average flow is steady. This test case was designed to approximate an experimental study reported by Klansky and Robertson titled Closed Conduit Flow. The relevant data obtained in the experimental study are the air-to-water volumetric flow rate ratios versus the Freud number of the incoming flow. The data is represented by the empirical expressions shown on this slide. For the case simulated with the Freud number was 3 and the average computed ratio of flow rates was 0.018, which is compared to the above formula's value 0.0174. The computational results is about 3% high, which is easily within the scatter of experimental data. Thus, the computations are in excellent agreement with the data for 10% sloped conduit. Another hydraulic structure we look at are fish ladders. And we'll now jump into our two feature stories, the renovation of a fish ladder at the third dam on some brook in Sumsville, Maine. And after we will discuss the Smith Mountain Dam Spillway Performance Project. The proper function of a fish ladder is crucial to fish being able to migrate upstream. The reliability of a spillway under extreme conditions is important in preventing structural damage. Hired by Woodlot Alternatives, Blue Hill Hydraulics used Flow3D to evaluate a fish passageway in Sumsville, Maine that was built 60 years ago. The crumbling existing design of the fish passage was prevented the migration of alewife fish from the ocean upstream through rivers and streams to freshwater lakes and ponds. The lateral variation of the velocities in fish ladders contribute to the goal of enabling fish to climb them. The alewife fish swim at about 3 feet per second and are able to sense lower velocity zones. For a successful fish ladder, a key requirement involves the creation of contiguous pathways where water velocities do not exceed speed limits. Engineers at Blue Hill Hydraulics first needed to validate the accuracy of Flow3D. A solids model of the deteriorated fish ladder created by Woodlot Alternatives was imported into Flow3D and ran. Configuring the model required overlaying a mesh onto the imported geometry, setting a pressure boundary condition for the inlet and a continuative boundary condition for the outlet. Also, fluid properties were loaded from the database. As shown here, the flows of Flow3D model matched very closely that of the observed fish ladder, providing confidence that the simulation data was accurate. This validation simulation also provided detailed information as to the velocities in any given location, helping determine where the changes in the fish ladder designs should be made in order to help the alewife swim upstream. Based on the Flow3D results of existing design, changes were made to facilitate improvements to provide an easy, navigatable passage for the fish. The middle weir was designed to maintain the asymmetrical shape of the two downstream weirs, and its elevation was increased to equalize the hydraulic drop between them and the upstream weirs. The simulation results of the proposed design predicted the distribution of flow, water surface elevation, and velocities in the latter. Additional results showed velocities at different cross sections so that the water speed at various depths could be evaluated to determine the ability of the fish to pass any given area of the fish ladder. The revised CFD model showed that the proposed design would work as intended and renovations would allow LY fish to safely negotiate the fish ladder. The revised model could also be used to simulate fish passage performance over a range of conditions, which is important because of the variations in river flow that occur throughout the entire migration period. In conclusion, the restoration project for the third dam fish passage was performed as a collaborative effort between Blue Hill Hydraulics and Woodlot Alternatives. Renovations were completed in September of 2006, and as shown here, the flow simulated in Flow3D matched closely that of the renovated ladder. Our next will be evaluating spillway performance. American Electric Power revised the probable maximum flood conditions for the Smith Mountain Dam located in the Roanoke River in Virginia and needed to determine if these conditions would adversely affect the spillway structures. The projected flows are as high as 120,000 cubic feet per second with a pool elevation of 822 feet. The original design was for 50,000 cubic feet per second and an elevation of 812 feet. American Electric Power contracted Alden Research to make this determination, who used Flow3D as their tool for simulation. The use of simulation reduced the cost to approximately 20% of that of experiment. Modeling took only 8 weeks rather than 8 months as expected. Starting with as-built drawings that AEP provided, Alden used a third-party CAD software to create solids models for import into Flow3D. They then meshed the model in Flow3D as a low-resolution model, a medium-resolution model, and a high-resolution model at 13 million computational cells. The idea was to quickly get a steady state conditions by simulating a low resolution version, then starting with the medium version and finally the high resolution version. With each case, the appropriate boundary conditions and initial fluid state and fluid properties were also defined. To validate the model, Alden compared the computed lake levels and flow rates with the discharge curve developed from a previous physical model data. The simulation predicted lake levels within 5% of their physical model for a given flow rate. Alden also created visual images for comparison at matching camera angles of those taken of the experimental data. Upon validating the model, the engineers at Alden then raised the lake level to the 822 feet above the mean standard level, which correlates with a flow of about 120,000 cubic feet per second. At this elevation, the water overtopped the dam by 6 feet and the spillway crest by 27 feet. Next, Alden compared the trajectory of the previous design flow of 50,000 cubic feet per second with the new conditions. If it was found that the trajectory extended 5 to 10 feet vertically down the spillway past the impact point observed at 50,000 cubic feet per second. The impact location was still 30 vertical feet from where the change in the catch chute begins, which is well within the region of the chute that was designed for the water impact. Also evaluated were other sections of the dam. It was found that the maximum movement and trajectory was about 20 vertical feet and remained at least 20 feet above the bottom of the ideal landing area. American Electric Power and Alden Research gained many benefits through using simulation as a tool for evaluating the spillway structure of the Smith Mountain Dam. A wealth of technical information was gained from the study, and at the same time, the costs associated with such a study were 20% of the projected cost for the experiment. The numerical modeling was completed in about 8 weeks, much less than the 8 months projected for building and testing a physical model. I'd like to thank you for your time today. We'll finish this by changing over to my colleague, Dave Souders, who will finish up the presentation for us.
Thank you, Travis, and thank you for everybody for attending today. First, in summary, as can be seen in this presentation, Flow3D can provide valuable insight into critical parameters of a wide range of design problems in hydraulics engineering. CFD is a beneficial tool for quickly testing designs and finding potential problems, and this presentation demonstrated how customers were able to improve a deteriorating fish passage and determine if a revised probable maximum flood condition would adversely affect a spillway. We also covered a couple of our core strengths, primarily how quickly a model can be set up because we make meshing simple with our favor method, and that Flow3D can accurately simulate free surfaces, and that is key in many hydraulics applications. If you'd like a demonstration of Flow3D interface and its capabilities, please feel free to contact us at the information shown here. And thank you for attending our webinar. What we'd like to do now is get to the question and answer part of this and answer as many questions as possible. And whatever we do not get to, we will follow up with everyone through email or phone. So let me see what we have here. We've had a number of questions coming in. One question is, for submerged horizontal jet, do you use one-phase model or two-phase models? And depending on those questions, there is a phase for the fluid and the sediment itself. And the sediment is a scalar quantity stored in computational cells, and it defines the property of the sand or whatever material you're eroding. And it's affected depending on a number of properties like density and shear parameters and so on. Let me see, bear with me here. Another question is, do you only use air entrainment or density evaluation? And Flow3D can run in two modes. You can look at just the air entrained quantity and ignore the bulking effects if the overall volumetric effects are not important. Or if you do consider them important and you need to look at the bulking, you can add the variable density model and look at the volume change of your fluid due to the air. Another question, what is the exact equation used for the air entrainment model? Well, I believe, derived this equation ourselves, and we do have a tech note available on our website. But what we do is we look at surface disturbing effects like turbulence at the free surface, and we compare that to surface or stabilizing effects, including gravity and surface tension. So we look at that balance, and depending on the ratio of the two quantities, we decide how much air is entrained. And then on top of that, we've added enhancements for jet impingement when that's important. Another question is, do you have any references for studies where Flow3D is used successfully in calculating sediment transport in an alluvial environment? And I'm not aware of any, but that doesn't mean we won't have any, and I will find out and get back to that further with everyone. We have a number of tech papers on our website, and there could be something there. Another question, when initializing the region of sand, is it enough to only change the flow density into sediment density in that region to looking at as sediment particles? I'll have to think about this question a little bit. I'm not sure I understand that. If Travis or Cheyenne has any further insight, feel free to let me know.
Could you repeat the question, Dave?
Let me go back to it here. It says here, when initializing the region of sand, is it enough to only change the flow density into sediment density in that region to looking at it as sediment particles?
I believe there are a number of parameters that one needs to define a sand-packed region, and typically these include the density of the particle itself and the solid fraction, which gives you an idea about how well the sand is packed in that area. We also look at numbers like the critical shields number, which tells you what's the probability that the sand would erode given a certain flow velocity and pressure condition. So usually there are several parameters that one requires in order to define the sediment region.
A follow-up question to that is, does the sediment modeling allow us to have a size distribution of the sand? Absolutely, we can have a Gaussian distribution of the mean size of the sand particles, and so we can make that as fine crushed sand or as coarse sand as you can find on beaches and such.
Thank you, everybody. Another question, which I think I'd already answered in another manner, but I'll go through this one too. Is there air treatment value under which we can neglect the density effect? And yes, the model, as I was saying, can be run with or without the volumetric bulking effects. Somebody is asking about multiple component capability, and we will have that in our next release. And what that means is we can simulate a combination of erosion type soils, and I believe that would be different layers of sediment that might erode. So if you had some sort of information about the different types of sediment at different depths, you could import that into Flow3D and then set the effects for each, or the parameters for each.
Dave, we have another question here that talks about can we model the flow through a fish screen, basically a perforated steel plate that blocks a flow. And that's absolutely, as long as we can associate this plate or screen with a thickness so we can resolve it effectively with our computational cells, there's no reason why we can't model the velocity and vortices that are due to the fish screen to prevent any fish or being trapped or lodged next to the screen.
And we do have one other option too. Fish screens could be done with baffles, and as long as you know the porosity and can properly define the drag effects, you could use baffles and have a two-dimensional plane that looks at this drag. Here's another one. Can Truvoff model surges or transients in large sewer tunnels? And absolutely, Truvoff is going to be accurate surface modeling, transient surface modeling for any type of free surface problem. And let's see, size distribution of sand sediment for sediment modeling, and I believe Travis just answered that. Another question, do you have an example of two fluid simulations? I don't have any examples handy, but I'm sure we do have something, and I will get back and find it and get back to you. And it depends on the problem type that you're interested in seeing too, so I will find out more. Another question, does the sediment model include the effects of wind? And no, it would not. Wind, you can include the effects of wind on your fluid surface, but not the effects of wind on the sediment underneath the fluid surface. Another question, can this program handle pressurized pipe networks? Well, we could easily simulate flow in a pipe. A piping network would not be well suited for this code. And let's see, here's another question. How do you specify the flow rate directly to a given boundary? And Flow3D now has a volumetric flow rate boundary condition where you specify the volumetric rate and the vector components to set the direction of the flow. And then one other point to add is that you can set a free surface at the boundary to control the flow elevation entering. Another question here, who else is using Flow3D in hydraulics applications? We have a number of customers, and I'll just mention a few here. U.S. Geological Survey would be one. Another would be Hydro-Quebec, and then Manitoba Hydro. Another question is, how much training is needed to become an efficient user of Flow3D? Well, we offer a 3-day training class here in Santa Fe for customers that purchase or lease the software, or somebody that wants to pay individually can also attend. And it consists of starting with the basics, where you learn, what does it mean to do some modeling, how do you mesh, how do you set up all the appropriate parameters, and it goes all the way to helping the customer set up their specific problems by the time they leave. And then is there additional help available after training? Yes, we offer technical support as part of a customer lease or permanent license. And support is responsive here, and you can continually reach the same person, which is pretty nice in today's automated world of support. Another question, how is turbulence modeled in Flow3D? Well, in Flow3D we've implemented 5 different models. We have Prandtl mixing length, 1 equation, 2 equation K epsilon and RG models, and then large eddy stimulation model. Our formulation includes the influence of fractional areas and volumes, the favor method, and that generalizes the turbulent production or decay associated with buoyancy forces. And I think that's about all the questions. Bear with me. Here's another question. Does Flow3D have mesh adaptation capacity? Well, our meshing is probably different than what most people are used to. Ours is what we call grid independence, so somebody can overlay a mesh on top of their geometry, and it's a fixed mesh where we break cells into area and volume fractions. One thing we can do is carry it a little further by adding multi-block to maybe set regions of higher resolution in areas that are of interest. But the mesh does not change dynamically with time. And then can we model, another question, can we model air back into the atmosphere from mixed flow on a chute? And I believe, I need to confirm this, but I believe Flow3D will allow air that is trained to leave the surface again and go back out into the open environment. At this point, I would like to thank everyone again for attending, and we will go ahead and close this webinar.